Hi, welcome to the fifth video here. We just completed in part 4, or video number 4, we completed the generation of the core classes of the program representation. Now we have to actually take the parsed concrete syntax tree and then from that generate an abstract syntax tree and then perform static analysis on it. So the static analyzer is the core of the compiler, and as such, there's going to be 2 videos on it. The first one, we're just going to kind of produce the AST without worrying too much about the checking or anything like that. We finished the last video and producing all of these core classes, programs, print statements, assignment statements, functions, you name it. We got pretty much all of them, and we saw that all the tests still pass. So let's get ourselves to a position where all that stuff is committed. We'll say the core classes right here, and then we'll begin our work on the analyzer. So as before, we're going to create a couple of files. We'll put the analyzer in analyzer.js in the source folder, and then we'll do analyzer test.js in test. And let's see if we can do a little bit of testing first. Okay, so what does an analyzer test require that we do? So let's just say that the analyzer does what? Well, there's going to be a handful of tests. We should do what we did with the parser. And maybe if you remember in the parser, we said, here's a list of syntactically correct programs. Here's a list of mistakes that we could make. We'll do the same thing here with a number of checks, things that we want to work and things that we don't. But we also would like to build in just to check that we built the correct program representation. So why don't we just say it builds a proper representation of the simplest program. I wonder what the simplest program. The simplest program would probably be printing a 0, perhaps. So why don't we say something like let's get a representation. What do we call it? An IR, a representation, an abstract syntax tree. And I'll just call it a representation. And we'll analyze. Maybe do. So if we call analyze on the parse of some program like print 0 semicolon, we should assert. Let's do our imports over here first. Import assert from assert strict. Yeah, let's import from assert strict, and let's import our parse from so C, where is parser? That was in parser.js, and the analyzer, well, that's going to come from analyzer over here. So let's just put this in place right now. Export default function analyzer, and that's going to take in the match from the parser, and it's going to return the representation of the program. For now, we'll just return a new program. Program comes from core, so let's just say return our core.program, and it will be, we'll just do it empty for right now. And let's remember to import everything from core as import star as core from /core.js is how we do it. Okay, and then we should have program. It's understood coming from there, right? Because analyzer's here, and then core is there, and then core has a program in it. Or wait, it doesn't. It does not. You know what we forgot to do over here? Well, that was pretty embarrassing. We forgot to export everything. Okay. Now that we put an export on everything, if we go back to the analyzer, we can hover over program, and it will say yes. Program is actually a something. Well, that's close. Okay. All right. Now for the analyzer test, let's just assert that this rep is equal to this when we parse it. See, right now we're just making sure that our things right. We're going to get back an empty program. So for right now, we'll just assert that this is equal to a new core.program. Did I forget my new over here? No, I forget. I remember new. A new core.program like so. And since we're doing is, assert equal is not going to cut it over here. We're going to be comparing trees or graphs or something. So we need to do a deep equal. And let's npm test and see that that actually does work. And now we got some issues over here. Analyze is not defined. Give you one guess why. Analyze from analyzer. Okay, let's try that again. And let's see, still got a mistake. That's good. Core is not defined. Okay. Import core from same src. Core.js. Is this going to do it? Is this going to do it? No, because we're not importing core. We're importing everything from core. So import everything from core. Let's do the imports right. This is JavaScript 101. Maybe 102. Okay. Now we got things passing. That's good. And then we have a lot of stuff uncovered in core, and that's not surprising because we have to deal with it. Now, when we're doing print 0, this is not exactly the thing we want. I mean, what we want here is that this program is going to have one statement in it. So the array is going to say, this is going to be a new core.print statement. And it's printing actually the argument, and that's just going to be the value 0. So this is the actual thing we want. And when we run the test, we'll see that that's not going to be what we're going to get. We're going to have a failing test as expected, because what we actually got back was an empty set of statements, but what we were expecting over here was the value here, print statement was 0. So it is now our job to actually implement the analyzer to work. And the test is set up for this. Let's get things going, and then we'll write in a whole bunch of tests like we've done before to check all sorts of abstract syntax trees and all sorts of semantic checking that we need to take place. Okay, so now to do the analysis, we have to get deep into some of the features that OHM gives us. One of the things that OHM will let us do is process the concrete syntax trees or matches that it produces. And you remember when we did the parser actually returns a match result object. If I hover it over here, it says this is an OHM match result object. In the analyzer, we want to take this match result object as such, and then we want to process it somehow. And we process match objects with something OHM calls the semantics object. So I want to build a semantics object here. I'm gonna make one called analyzer. So I'm going to make an analyzer object. We'll see in a minute how I can turn this into an OHM. Okay, I don't know. I'll just put null here just to get something in here. And then what we're going to do is we're going to take the analyzer and we're going to give that the match object. And then we're going to put an operation on it. So the full syntax over here I should say not the full syntax, but the thing we want to do for our analyzer is, let's see if I remember, it's basically, we have a semantics object, create semantics, but we're going to apply that to the actual grammar. So first we have to actually get the grammar. So we go into the matcher, and from that we can get a grammar, and then we invoke create semantics on it. And on that semantics object, we add an operation. I'm going to call this operation REP for representation. And that is going to be an object. And this particular object is going to have in it one method for each node in the concrete syntax tree. So how do I explain all that? All right, well, let's make some room here. And I'm going to put this on the left, split left. close this down. And it's going to work something like this. In this semantics object, we're going to have for each concrete syntax node, like including program. Program is going to be a method in here. Statement doesn't have to be, because statement just has one thing in it. So we can drop down to print statement. It's going to be a method for this. And there's going to be a method for assign statement. Each of these are going to have their own method. And they're all going to be inside of this rep operation. So the way that this thing is structured in OHM works something like this. You create a semantics object for a given grammar, and we're going to fetch the grammar directly from the match, which is fine. And then we add an operation to it. And what happens is every time OHM is asked to use this semantics object, you give it a match, and then you say invoke this operation. The operation we're going to invoke is rep, and we're going to make sure that for program, we're going to return here a proper abstract syntax tree representation, okay, for all of these things here. Now, each one of these operations has in it the thing on the right-hand side. So since program is on the left-hand side, it's going to be a method, and then the statements are going to be what is passed in. For the print statement, we're going to take in the print keyword, an expression, and a semicolon. So the print keyword comes in, and then an expression comes in, and then a semicolon comes in. This is the way all these things are actually built. For an assignment statement, we're going to get in a variable, we're going to get in the equal operator, and we're going to get in an expression, and we're going to get in a semicolon. I'm using underscore, doesn't like var because that's a keyword in JavaScript, so let's call it variable. Yeah, it doesn't, what I'm using is I'm using these underscores because underscores are a way to, mark in JavaScript a function that the editor over here, VS Code in this case, is going to ignore the fact that we don't use it. I mean, we really don't need to use those things. For variable declaration, I'm looking over here, we're going to get the let keyword, we're going to get in an ID, we're going to get in the equal symbol, we're going to get in an expression, and we're going to get in a semicolon. And what I'm going to do right now is I'm just going to add in the rest of these things, and then we'll talk about them. Okay, so that's done. So what happens again is for each left-hand side of these rules from the grammar, we have a method inside of our semantics object, which takes as parameters each piece of the right-hand side. So while statement has a while keyword, an expression, a block. See the while keyword, an expression, and a block. In some cases, you'll notice some interesting things about them. For example, how the colon and type here are in a question mark. So when OHM actually processes these, it's going to give us an array of colons and an array of types. And the array will be empty if we haven't used anything here, or it will be an array of one colon and an array of one type. So that's why I've written colons and types here. Otherwise, nothing is too surprising. You can see that I've left some things out here. I did go down for, say, when we're in term, for example, term binary. You can see that terms can be have a binary form, then they have an unmarked form. When term goes directly to factor, we leave that out because if OHM sees a term that's made up of a factor, it's going to pass it right through. But if it sees a term with a factor, we're going to take the binary portion of it. And you can see that each one of the rules in OHM that have a tag on them, well, that tag appears as an underscored suffix over here. So term binary, the term with the dash binary is going to be term underscore binary. And you can see similar things with, variable subscript and type underscore array becomes type array, exp binary goes here. The variable subscript actually just wraps around, but you can see that it sits right there and it shows up like so. Now, some of these things, like for keywords and some of the things I don't really have in here, but I did put in a rule for true and false, and we'll see why that is later. But at this point, what I want to do right now is let's put this back. Let's get rid of pigeon.ohm, and we'll take a look at our analyzer and then how it works. So the idea here is that this analyzer is an ohm semantics object. It's going to be passed match, and we're going to look at the rep operation. And right here, I'm just going to, just so we can see everything working, I'll return a new core program object. And we want to pass the statements through, but I won't be ready to pass the statements through just yet. I'm going to leave it here as empty. And I want to run the test just to make sure that we don't get any noise from ohm about problems that we may have. And you do see that we do have one. Look, errors in the x60. var underscore ID is not a valid semantic action. So we did something wrong with the var and the ID. Oh, yeah, you can see that for var, I have a subscript, but then I have this one form right here that I wanted to capture as a special action. We'll see why later. Yeah, I'm jumping ahead a little bit because I know from experience this is something that you want to do. So let's do var ID now. And now let's see if we want to make sure that everything is set up properly. We do have errors, and the error we have here, oh, good. The only error we have right now is that we're not getting the thing that we expected. We expected to get back a print statement. So our job right now is to walk through each one of the analyzer operations and build the thing that's actually expected. So for example, for a print statement, what do we want to return? If we get a keyword print and we get an expression or we get a semicolon, then we'll want to be able to return a new core dot print statement. We have a core print statement there. And what are we going to pass to it? So we actually need to recurse through this tree. Fortunately, ohm does a lot of the engine of working the tree kind of by itself. If we take the representation of this expression, that's the thing we want to put into the print statement here, because whatever is produced by computing the representation of this expression, that is going to be the argument for the print statement. And so building up the abstract syntax tree is really just a matter of walking through each one of these things right here and doing the recursion that's necessary. So, sometimes it gets interesting because here for the return statement, remember the return statement, we went ahead and we put in let me find the return statement here. We went ahead and we made this thing optional. So this is actually going to be an array of things. So why don't we just work on that a little after? What can we do for blocks and binaries? Are any of these things pretty easy to do? I think I think some of these binary ones are pretty easy. We can just return a new core binary expression with the condition 1.rep, the relational operator. Okay, now the relational operator is going to come in as a syntax tree node, but we just want its string. We just want to take its the string representation of the operator, because everything that comes in here to these ohm semantic operations are chunks of a concrete syntax tree. If we call source string on them, that means that we actually want the text. So if this was a less than operator, we're getting passed in a concrete syntax tree node with a less than operator, but we actually want the string. So it's going to look something like this. And then condition 2.rep would be the other operator over here. This is good for now. Later, we're probably going to split this out, and because we want to do some type checking on it. I guess if we're in the mood to look ahead a little bit, let's try that. Let's do condition 1.rep, and then we'll do write is condition 2.rep, and then the actual operator that we want is going to be the source string of the input rel op, source string. And then we can, and that, by the way, this is a property while rep is a method. Then we can just go with left operator. Ooh, how did that happen? Left operator and right. And we're leaving open a chance that we're going to do some of these things. We're going to clean these up later. So we can go through and do similar things here, although this is going to be an expression, and this one's going to be term, and this is going to be our just regular op. Save that, let's prettier do its work. Okay, for numbers, the syntax of numbers were a certain number of digits before the decimal point, then an optional decimal, and then there's a fractional part, and there's an E and everything like that. We really don't care about all that stuff. In Ohm, you can just grab all those, you don't have to worry about all those little things. If you want to just take the current rule source string, you have access to that whole thing. And since numbers in Pigeon look like numbers in JavaScript, you really don't have to do much. All I really want to do is convert this to a number. So I'm going to take whatever the text was in Pigeon, just going to make a JavaScript number off of that. And I'm going to do the same thing for string literals too, only this time I really don't need to worry about the converting it to a number. For true, we're just going to return the JavaScript Boolean variable true. That's going to be a direct representation. And for false, we can use a direct representation of that as well. Anything interesting? I guess for blocks. Okay, blocks have a sequence of one or more statements. Okay, so we have an actual list of statements. This statements thing right here that's getting passed in, this is going to be an actual concrete syntax tree node. The individual statements are not, this is not a list of statements in them. This is a node whose children are the individual statements. So believe it or not, what we want to do here is something like this. We want to take each statement in the children of statements. So again, this is a concrete syntax tree node. These are the children of that node. And then for each one of these things, we're going to return its representation. So block works like this. As a matter of fact, this is how blocks work. Programs are going to actually work the same way. So we're going to build a new program whose statements are, let's clean this up. The statements are going to be all of the process statements from below. That's how it works. We're going to build a program, and then we're going to take each statement in statements children and put that together. What else is interesting? What about the while statement? Return new core. Yeah, core dot while statement. The expression is going to be the test. So, we're going to eventually check to make sure that's a Boolean. So let's just think ahead a little bit. Let's just think how to say const is going to be the representation of the EXP, and the body is going to be the representation of the block. And then we can just create the while statement with the test and the body. Wow, this gets a little bit tedious, but there's a lot going on here. I'm going to fill in a few more of these things, and then we'll come back and deal with the hard stuff in a minute. Okay, I've dropped in a few of the basics. So all of the binary expressions, I took the same pattern of using the left and the right as being the reps of the input. So we have a left and right for the expression term for the additive operators, and then for the multiplicative operators, left and right are going to be, the term and fact respectively. I have the exponentiation operator handled over here, and the negation. I have a few of these going on here. Okay. Now let's do some of the ones that are a little bit harder, like the return statement. So we know that the EXPs right here are, as I mentioned before, because the expression is optional, we're going to have an array here, which is either empty or it's going to have an actual value in it. So what we want to do over here is to say, well, if I do EXPs and if I look at the children right here, the children of EXPs, this is either going to be empty or not, right? So if this is actually empty, so we can say something like, if this thing right here has a length, which happens to be 0, then then my return statement is not going to have an expression. Otherwise, it is going to have an expression. And this is a good opportunity to go back to the core and realize that in our return statement, which is right here, there's actually two kinds of statements. There's a return statement with an expression, one without. Now, we could store a null value in here, but nulls are pretty evil, and we like to try to avoid nulls the best we can. So let's talk about the idea of having a short return statement as one that actually doesn't have anything inside of it. So we'll just say here, this is intentionally empty. So short return statements won't have anything in them. That way, in the analyzer, we can just return here a new short return statement. There we go. And otherwise, we can just return a one with the exp rep. So now how are we going to get that? Well, let's return a new return statement. And right here, our expression is going to be exps dot children. And it's going to be the first child, and we'll take the rep of that. And that's how we deal with this case of having the optional thing here, right? I think we also had an optional for our function declaration, right? We said that the colon type was missing also. So this is just going to give us a little bit more work to do, right? We want to eventually return a function declaration and a function. But here's the thing. If you remember back to the pictures that we made. Yeah, specifically here, we had a function declaration, but the function declaration and the function were separate entities. Now, in our grammar, we only have a rule for function declaration. When we encounter function declaration, we want to build a function declaration and we want to build a function a function also. And we want to do the same thing when it comes to variable declarations. So we have a variable declaration, that's our syntactic category, but we'd also like to build a variable the same way. So doing the variable declarations and the variables and the function declarations and the functions are going to take a little bit of work, but they're not hard. They're just a little bit. So again, not hard, but tedious. Let's take a look first at the variable declarations. Okay, so when we see a variable declaration, yeah, we definitely want to get the initializer. That's the exp rep, right? So let's take our initializer, and that's just going to be the representation for the rep over here. And we want to go, yes, we do want to return a new variable declaration. That's from core. And variable declarations in core, VS Code is helping us here, has a variable part and initializer part. So a variable and the initializer. But what is the variable? Well, we're going to have to make a variable. So we say new core dot variable. And what do those things need? We need a name. And the name is going to be the identifier's text, the source string of the identifier, right? And then it's type. Okay. Well, here, we don't yet know how to do type checking. Type checking is going to come in the next video. So the best thing we can do here probably is to leave a placeholder right there. In fact, we can probably just ignore it and it will just show up as undefined. And okay, we are using JavaScript and not TypeScript, so that's okay. We can just leave that open. In fact, you probably noticed that for binary expressions over here, we're leaving the type out too. We're going to do types in the next video. Right now, we just want to make sure we have a structure in place and that certain things can work. Oh, assignment statement, return new core. This was one that I think was simple enough that we could have done earlier. The variable rep here and the exp rep for the source. Okay, got this one here. So we got program, print statement, assignment statement, variable declaration, function declaration. It's going to require a little bit of work. We're going to eventually return core function declaration, and that's going to take a function, I'm calling fun because function's a reserved word in JavaScript. So what are you going to do? And then the body is going to be the block, the representation of the block. Now, the function itself is going to have what in it? A function needs a name. That's the source string of the identifier. It's going to have params, so params rep. And the return type is going to be, okay, so here it says cool as a type. Again, we have a case where this thing is actually optional. So we got to deal with this thing somehow. So how do we deal with that? Well, again, types may have children, and if there are no children, if types.children length is 0, by the way, there are ways to clean this up or make it a little bit more efficient. I'm just being a little bit direct now. Then there are no types. So the return type for this function, we just, we can do it like this. Now, I don't know if we should mute. Actually, we probably, you know what? We probably should not do mutation. Let's just try and get a good return type here. Return type. And well, if there are going to be no children, we'll assume that we have a type called void. So core type void. And a matter of fact, let's just pretend this may not be the best way to do it. But let's just assume right here it's void. And then if it is bigger than 0, that means we have exactly 1. And so what we can do is we can say types 0 dot rep and just take the representation, whatever that type is. And then we can just put in the return type. Return type is going to be this thing. And so perhaps, we should probably do JavaScript a little fancier over here, right? You might want to say, should we use a ternary here? If types children dot length is equal to 0, then we want void. Otherwise, we want the rep over here. Prettier will fix it for us. You are using Prettier, I hope. There we go. If type was not specified, we're going to call it void. Otherwise, we'll just return the rep of the first one we get. So why did I put in type void? Like, what am I even doing over here? Well, let's go into type. Oh, I called it basic type. I can just call it type. I don't think anybody will care. Let's put in a static void and just say this is a new type whose name is void. And that will be the name. Or if not the name of the type, maybe the description of the type might be a better word for that. That's what I was using earlier. Okay, so yes, we do have type.void as a way to say nothing. Later, we're going to show how to take words like int and boolean and string and turn them into better types. Anyway, I kind of have a big mess over here. At this point, let's run our test to make sure we haven't broken anything beyond repair. And it looks like we got lucky. We have not broken anything, but of course we do have uncovered stuff in the analyze from the core. But what we've done so far is, we have to do a couple more things over here. Let's build out a parameter. Let's return a new core variable. Variables have a name. That's the source string of the ID. And they have a type. We'll just put in the type rep here. For params, we have, this is going to be a list of params. Here's where something gets pretty interesting. Look at the grammar here for params. Params has this thing called list of in them. So it's a list of parameters separated by commas. When you have list of, we did not say param star or anything like that. We said list of. When you do that in OHM, the expectation is that you call as iteration on it. As iteration, and that will give you something that has children. So whenever you have list of or non-empty list of, remember you do as iteration and children. Then we can map over this and we can take each one of those parameters and we can return a new core dot variable whose name is P's source string, and the type is, what is the type? Oh, it's whatever the parameter type is. Oh, we don't need to do all this. What am I doing? I'm making a trouble mess over here. It's just, we just run the reps on this is all we have to do. We just take the representation for each one of these things here. And I have way too many parentheses. Okay, I think that's it for everything except for the subscript, which is not too hard. Return new core subscripted expression with the variable representation. I should have done this one earlier. And the subscript representation is, yeah, exp rep. And for the variable ID, right now, I'm just going to return the ID source string. This is going to be, this is actually going to be a lookup, because we want to make sure that if we ever see an identifier, that it has been previously declared. But right now, we're just trying to get a tree put together without breaking anything. So let's run our tests. And by the way, did you notice that these tests are passing now? It's passing because in the analyzer test, I only have a very, very simple test here, which is that can understand print 0 to give back a print statement with a 0 in it. We actually already handled this in the analyzer. But what I think I can do right now is I can stop because this video is long enough. And we'll begin the next video where I will have entered a number of test cases for the tree to make sure that they work. We'll run tests, we'll clean up the tests and do all that stuff because I'm sure there's probably going to be errors. But this here is probably a good place to stop. We do have passing tests. And as always, if you get to a good stopping point, git add, git commit, and we're going to say first pass, or you know what, a lot of people like to say work in progress, right? Just started the analyzer. For part 2, we're going to test it, and we're going to do the actual static analysis. We're actually going to do the type checking and make sure that the variables were previously declared and all that good stuff. See you then, and thanks for watching.